Okay, so in the last class, we saw CTL star, okay, as a temporal candidate, a temporal logic candidate for specifying properties of the kind that we were interested in on Kripke structures. And saw this formal syntax and semantics description of CTL star. And we started to see some examples. We'll see more examples today. So just to do a recap, so the semantics of CTL star and even model checking of CTL star is defined in terms of by defining a satisfaction relation for the well-formed formulas of CTL star for a given Kripke structure M, along with a state and a path phi in it. So we saw that there were two kinds of formulas that CTL star formulas were built over. So one was the class of path formulas whose satisfaction is defined in a Kripke structure, is defined for a given path phi. So a state formula, the satisfaction of a state formula is interpreted, is defined with in a Kripke structure with respect to a state. And a CTL star formula was a state formula, well-formed state formula. So model checking in CTL star is denoted by this turnstile relation. So we say that a CTL star formula psi is satisfied by a Kripke model M if and only if the following condition holds true. For every state, for every initial state, S belongs to S naught, MS, psi is satisfied by that state in the initial state in M. So just as an observation, so as per this definition, it is possible that a model can both, it may not satisfy both psi and not psi. Why? Unlike classical logic, in which either the negation, like propositional logic and first order predicate calculus, classical versions of them, psi, one of the two holds good because of the, usually that's either psi or not psi is guaranteed to be true. That principle is called the principle of excluded middle, whereas the satisfaction relation is that property does not hold. Why? Can you? Anyone?
Like psi could be satisfied for one state and not of psi could be satisfied, like not satisfied.
Exactly right. Yes. So it may be true for one of the initial states, but not true for another initial state. So it could be that it is true for some, initial state, but it is not true for another initial state. Therefore, for instance, the definition, it's just by the definition, that's all, since we require that it hold good for every state that satisfies the initial condition. So this kind of, by definition of what model checking is, this condition is possible. Now, given two formulas, phi and psi, CTL star, or for that matter, any of the temporal logics that we will later define. What does it mean for two formulas to be equivalent? As a matter of fact, what does it mean for two formulas in a classical logic, like propositional logic or predicate calculus, for them to be equivalent? Amin? What is the answer for, say, a formula in propositional logic or predicate logic? Amin? That's a question for you.
Yeah, like, I'm thinking.
Okay. See, this question can be answered in two. Yeah, go ahead.
For all interpretations, both should be same.
Exactly correct. Exactly right. That is what is called a model theoretic implementation. For all interpretation, for all models, okay, if phi is satisfied by model, if and only if, okay, psi is satisfied by the model. Now, that is what, okay, I call it the model theoretic way of defining. Of course, what is done is there's a proof theoretic way of answering that question as well. Usually, what is done is once you define what the semantics, the formal semantics of a particular logic is, or the formulas in the logic, you normally define what are called inference rules, okay, and that are used to derive from some consequences from a set of other from a set of given formulas, starting from set of given formulas, infer another formula, and usually you give certain rules of inference that can actually be used to derive consequences, prove that a particular formula in the logic follows as a consequence from a given set of formulas as assumptions. So one can also say that these two formulas have to be derivable from no assumptions, okay? Starting from no assumptions, you should be able to, or you should be able to derive, you should be able to derive psi starting from phi and vice versa using a set of inference rules, okay? And actually those inference rules have to be relative to set of inference rules. You can also define what it means for these things to be equivalent. And usually you might recall these kinds of notions must have been defined by Kumar in your course on logic. These inference rules are said to be complete, okay, if whenever phi and psi are equivalent as per the model theoretic interpretation, as Amin described, then if you should be able to derive the one from the other using those inference rules, then that set of inference rules is said to be complete. Okay, so these are side observations that I want to make. Okay, so in that sense, the model checking is kind of different from the doing proofs in a particular logic, but then but because it is the task of model checking is to show a satisfaction relation that given a particular model. But you could see that you can also express this as a proof. We can also derive it as a proof if indeed you're able to describe the model itself as another set of formulas in that logic. Then you can express the satisfaction, the model checking, which is a satisfaction relation also as a way of deriving proofs. But that's an aside. Okay, so what I'm doing is, since you've studied logic, you've done proofs in logic, I'm just trying to contrast what model checking is relative to proofs. I hope you understood, appreciated that point. But model checking itself is the task of given a formula in a logic, okay, then a model, okay, then it is the task of automatically, that's what we are interested in, to show that the model satisfies psi as per this formal definition of what model checking is. Okay, so any questions there? I hope it's clear. Okay, I mean, as an aside, I was saying this whole model checking problem can also be posed as a proof theoretic problem as well. But in this course, we will be studying algorithms for model checking, for algorithms for exactly deciding this satisfaction problem. Yeah, but anyway, so, I mean, okay, now what does it mean for two formulas in CTL star to be equivalent relative to this model checking? I've only defined what it means for, CTL star, for M to be satisfied. Now, if you want to say that two formulas are equivalent relative to this for a given model, then what it means is that for M, for every model that phi is satisfied by phi, then M psi should also be satisfied by that model. Okay, so that's how you would define. Since we are, so when you do proofs, it is for all models. Okay, so since we are here defining the model checking problem as a satisfaction problem, then these two things, you could say they are equivalent for all models for which phi is satisfied. So should psi be. Okay, so see that this is important, because when you do symbolic model checking, you will see very soon that there is a lot of redundancy in this logic. There are so many different ways to express. You can have lots of different formulas expressing the same property in the sense that they're all equivalent. So you will obviously encounter this question, okay, if two formulas are equivalent. And one way you can answer that question is using this, this way, that you will have to, formally, if you want to prove that two things are equivalent, then you will have to show that indeed that they are equivalent for every model that that one formula is satisfied by, the other formula is true as well. Okay, so in today's lecture, today's lecture, the outline. This is the outline, but at least for the next couple of lectures. We will first see, we want to get to equivalence in some normal forms for formulas in CTL star that I will get a little bit later. First, I will go through some examples of CTL star to get a feel, to help you get a feel for formulas in CTL star. Then we will define some sublogics of CTL star, specifically CTL, LTL, and ACTL and ACTL star. There should be ACTL. Okay, and then we will define safety and another classification of properties, which we had briefly alluded to in one of the earlier classes. I had alluded to in one of the earlier classes, a classification of properties into safety and liveness, and then we will revisit fairness in a formal way. And what does it mean? I've just now defined formally what a model checking problem is as a satisfaction problem for a given model, and what does it mean for us. We will also define fair satisfaction. We'll also compare CTL and LTL. Those sublogics are the most widely used sublogics for model checking, because CTL and LTL are, those sublogics. The model checking problem is, is fairly more efficient than the general CTL star, and that's why most model checking tools, they support CTL and LTL. But their expressiveness, we will compare CTL and LTL with respect to their expressiveness. Okay, so that's the plan for this class and the next class, hopefully. Yes, there was something, some chat here. Okay. Yeah. Sometimes if the bandwidth is an issue, maybe that's why I usually start your live stream, YouTube live stream. Maybe you could use, this is a general comment that I'm having. So YouTube live stream, if you could use that. It has lower bandwidth requirement, I understand. Okay, that is something that we can. No, this is not what I want to start with. Okay, so first I will go to, which one do I want? Okay, so this is the one I want. I guess Paramala is not there yet. Okay. We'll have to continue. Okay, so I want, I hope you could see this slide. So for each of the formulas that we used earlier in the last class, I want you to answer the following question. I mean, some of them is a path formula. If it's a state formula, give me some examples of states in this transition, in this Kripke model, for which that state formula is true. Okay, and if it's a path formula, I want you to show me some path in the some path for which in the Kripke model for which that formula is true. So let's start with this state formula. Since every state formula is also a path formula, let's say AB is equal to 0. When viewed as a state formula, what are some states for which it is true? Let me ask this question. When viewed as a state formula, show me some states for which it is true in this model. And viewed as a path formula, give me some paths for which it is true. Paramalai?
If it is viewed as a state formula, we can say.
Yeah, give me answer to both. Okay, if it's viewed as first as a state formula.
So every state which has the variable, okay, which has AB is equal to 0.
So specifically, this initial state,
yeah.
Both the initial states here satisfy, correct? Yeah.
Yeah.
And there are also several other states. You're right. Okay. So it'll be more interesting when viewed as a path formula. Give me some paths for which AB is equal to 0.
Every path which starts from the initial state.
Correct. Okay. And there are other paths as well. Correct. And any. Yeah. As a matter of fact, the path starts from 0, 0, 1. This particular one where my cursor is. Okay. So that is also true.
So just for clarification, here AB doesn't mean the multiplication, right?
No, it's not. I mean S dot A followed by S dot B. That's what I had to. Yeah. Correct. Yeah. So it is not multiplication. Okay, so moving on. G of AB is equal to 0. Ratnakar?
I actually forgot. Does G mean that every single state in the path satisfies it from that point?
Correct. Correct. So you no, see that, yes. See, first of all, this is a path formula. Agree? Yeah. So you'll have to. I mean, it's only meaningful to ask which paths. Okay. Having said that, so remember the way that the formal semantics. I mean, the way you said is correct. But since we are here, we're talking about the way this formal semantics was defined was relative to a path. It is satisfied by a path if by an infinite path, if every infinite suffix starting from I is equal to 0 is true for that, okay? Which is informally what you just now said, because after all, if you say that these paths are sequence of states, then one way of stating is, since they are, the subformulas are also path formulas, okay? A better way to state what you just now stated was, it is true of a path if the subformula is true for every infinite suffix,
Okay.
of that path, starting from 0, 1, 2, and so on, okay? That's the way it should be interpreted, in a formula, okay? So having said that,
There is no path that satisfies this one, because there is no path that loops on 0, 0 forever.
correct, okay? So no. I mean, let me give that. No. I'm telling you, if there is a path on this, for this. No. I'm asking this for the entire Kripke structure. See, in the Kripke structure, here I've only shown a part of the behavior. There is also a behavior. I'm only asking this question. I'm not asking this question, by the way. I mean, just to make it a little more general. If it is true for, I think your answer is correct. You are answering if it is true for this Kripke structure. So my question is, in this Kripke structure, if there is a path, okay, interpret it that way. Okay, if there is a path for which G of AB is equal to 0 is true, okay, interpret my question that way, okay?
I can't find such a path.
Why not? How about 0, 0, I mean, a path starting from 0, 0, 1, okay, in which reset 1 remains continuously, yes, 1. Okay, so for example, even here there is this path, the rightmost path. Let me look at my cursor. I hope you can see my cursor. So 0, 0, 1, and then 1. There is a path in which that reset remains 1 continuously. Okay, forever. That path certainly satisfies this JAB is equal to 0. Okay, specifically, there is a path starting from this initial state 0, 0, 1, okay, wherein starting from that initial state itself, it satisfies, correct? Okay, yeah, but I think,
sir,
yes.
Is there a formal way to specify that particular path that satisfies this formula G of AB is equal to 0?
No. What I'm saying is that is, I mean, this is the formal way. G of AB is equal to 0. If you ask this question, there are two ways to see. This is a formula, okay? By saying, give me a path that satisfies this, that's a formal way of doing it. I've already, the satisfaction relation, the way I've just now stated it, is the way to do. Now, it's another matter that model checking is a concept that has been defined relative to a formula being satisfied by a Kripke model. Okay, so there you define it in a different way. Okay, so you could define it. Oh, I mean, you will see later on when we concentrate on LTL, you can define it as every path starting from an initial state. Okay, I mean, you could define it like that. Okay, I think, yeah, I mean, I think the confusion is coming because I've defined satisfaction in a general way. I mean, you can either say, given a formula, you can say, oh, it is satisfied by a particular state, if it's a state formula, or a particular path. Okay, so then by asking the question, no, does it satisfy by this path? You already have that. Now it's another matter that we are extending the satisfaction problem to the entire Kripke model. Okay, then you will have to use something like, oh, if it's a state formula, and you have to extend that definition, and that's how model checking problem has been defined. Okay, so that is just so I hope you understand. Yeah. So yes. Okay. So right now we are just using those formulas as interpreting them as state formulas or path formulas, and I'm just asking the general question. I'm not asking it relative to whether it is satisfied by the Kripke model. Okay, relative model check. So we'll get to that. Okay, model check. So
also, this formula doesn't belong to CTL star, right? Because this is not a state formula.
That is true. That is true. Yeah, you're strictly right, because the way I've defined is CTL star as a thing, but it is a component of CTL star. That's a good point. That's a good technical point. Okay, as we will see, this belongs to the sub-logic of LTL formula. You're right. Okay, that's a very good technical point. Who was that who pointed that out? Okay. Yeah, you're right. I think we have technically defined CTL star. Although we have defined path formulas, we have made a CTL star as a state formula, and therefore it is not. It is not. Yeah. Okay. For the moment, let's view it as just a path formula. You're exactly right. Yeah. Okay. Moving on.
That question.
Yes.
I think you might have already said this, but in this, by path, do we mean path in the graph theoretic sense, meaning no state can be repeated?
No. What I mean by a path is a legal execution of
Okay, I just wanted to confirm.
Yeah. Which means that it is a path in it's a path in one of the behaviors. Okay. Because a behavior is defined as something induced by legal executions, right? Starting from some state. I mean, no. I'm sorry. Behavior is technically defined as starting from initial state, but I'm kind of here allowing that from any state. Okay, from any state. So for the purpose of this example, I'm allowing paths from any state. Okay. Legal executions from any state. Okay, for the purpose of this example, although a legal behavior in a Kripke model is limited to paths starting from an initial state. Okay, for the purpose of this example, I'm relaxing that. Yeah. So Ratnakar. Okay, so let's see. So f of AB is equal to 0. What are some paths? Either this behavior or paths from any of the states. Say, yeah.
We can take a path that starts from 1, 0, and then goes to 0, 1, and from there to 0, 0, and keeps looping.
Why only that path? Are there other paths?
So every path in the system is satisfied.
Exactly right. Exactly right. So that was Paramalai, I guess. So Ratnakar, do you agree with Paramalai? Actually, every path when I say path here, it's only infinite paths. Okay, so let's restrict to infinite paths. If they're finite paths, no, we're not interested in finite paths. Infinite paths.
Also, when we mean path means it will always start from an initial state. Right?
No. That I'm relaxing. Let's suppose we consider, for the purpose to be kind of consistent, that let's suppose my initials, I'm defining my initial condition as true. Okay. For the purpose of this example, let's assume that my initial predicate is true, which means every state is an initial state. Okay. So if we assume that, I mean, yeah. So as a matter of fact, every path, every infinite path, okay, satisfies this condition f a b is equal to is it? It does because either, yeah. See, if reset is asserted by one, in the next state, So what does f means? Okay, that means that eventually in that in that path. Okay, so either see in any of the paths, either zero reset remains to be zero, in which case it'll count. It'll keep counting. It'll keep counting. So it has to get to zero, or it has some state in which reset is one, at least one state, in which case the next state AB will be zero. In either case, as per the semantics of F, which only requires that at some point in the future on that path, AB has to be zero. Okay, so it's a matter of every path in this model satisfies that condition. So are you convinced, Ratnakar?
Yes.
Okay. So let's move on. I mean, so in that order that I'll take XG. So this is
X means the next, like the next pi of 1 will be satisfying the thing, right?
yeah, pi superscript 1.
Yeah.
Okay.
Superscript.
Yeah, the suffix it is true of a path pi if the sub-formula g of AB is equal to 0 is true of pi of superscript 1. Okay.
So g of AB equal to true starts with like 0, 0, 1. So we can take like the 0, 1, 1 as the starting of the
All right.
path.
So this is a path starting from 0, 1, 1. The
And going to
rightmost,
0, 0, 1.
yeah, the rightmost one is
Yeah.
one such one such path. Obviously, this is not true if you for this model. Okay, if my initial state is just these two states, correct? As a matter of fact, so certainly it is not true for. Yeah, I mean, let's not. Okay, so I mean, let's restrict ourselves to this, just to path formulas and things, huh? Okay, so correct. Yes. So the next one, moving on. So Ratnakar, EX of G. The next one. Let's move to the next formula. This is actually, this is wrong the way that I've said. Huh? This is a state formula. Oh, let me see if my. Let me see. So maybe I'm reading it. Correct. Since this is a state formula, so I'm asking Ratnakar, give me a state in the model for which this
Does
is
11, 0 satisfy it? Because you can go to 0, 0, 1 and loop there. So you have a
1111, 0. So say, let's look at this. This is, you can see my cursor, right? So 110 and 110. What does it say? That it says that it is true of a state if there exists a path originating from that state for which x of g, okay, which one are we looking at? Oh, I'm a little bit confused. We just did, okay, in any case, my question is exg, okay? So which one are you answering for, Ratnakar? Okay.
EXG, right? That's what you asked me, I think.
Yeah. So I kind of inadvertently skipped the previous one. Let's get to that. Okay. So yeah, let's just do this exg. So it is true of a state if there exists a path from that state for which xg, for the path formula, xg of ab is equal to true is true. Okay. So why if 1
You start from 11, 0 and then in the next state you go to 0, 0, 1 and then you loop on 0, 0,
Yeah,
1
so
infinitely.
that's right. So if you continue to hold reset 1, certainly there is a path of that kind, correct? So it is true of this state because there exists a path in which, although AB is not equal to 0 here, there exists a path in which from the next state onwards, AB is equal to 0 is continuously true. Okay, so this is certainly thing, and of course there are several other states. Okay, so you get the idea. I hope. Let's complete this. Okay.
I'm sorry, I had a doubt here.
Yeah.
Like this will work for any state 0, 0, 1, right? Because like it will have a path with repeating 0, 0, 1. Or should it be a different state and then the next one should be 0, 0, 1?
No.
Like 0, 0.
This will be true. It is certainly true for 110. As a matter of fact, this one is true for any state. That is. Yeah, I guess this is true for, as a matter of fact, this is true for any state in this thing, because from any state, you always have a state in which,
Yeah, like any state will have like reset as 0 and 1 also. So
yeah. So I guess in that sense it's true.
but I had the doubt about X, right? Because like X means the next one should be satisfying the given condition, right?
Yeah. What do you mean next one? Yeah. I mean, what it means
like pi
is
of 1.
pi of, yeah.
So the initial one is also satisfies the condition. Does it have a problem with
It
that?
doesn't matter. Well, whether it satisfies or not, it doesn't matter. It can or it may not. It's not required to.
Oh, okay. Yeah, that is.
So it only says that there must be a path from that state. Okay. There must be a path from that state whose pi one suffix should satisfy G. Okay. Of AB is equal to 0. That's all it says. Okay. There must be a path. There must be a path for which xg of AB is equal to 0 should hold good. What that means is that there must be a path for which g of AB is equal to 0 should hold good for pi of superscript 1. That's what it means. Yeah. Okay, so who's next to go? So let's do the last one and then move on. Or maybe we'll do what we skipped here. Give me a path where x of EG of EB is equal to 0 holds true. You know, Paramalai? I don't know who did it last time. Okay, but
Yeah. So the path that starts from 0, 1, comma 1.
0, 1, comma 1.
0, 1, comma 1. The rightmost path.
Correct. Yeah.
So from that, the next, yeah, the next state is 0, 0, comma 1, and it has a path originating from it which satisfies G of A is 0.
Correct. Yes. Yeah. So this is kind of different from XG.
This also, this formula is also satisfiable for every state, right?
Yes.
Because from every state, we can move to the next state, which has the reset as 1.
Yeah. Yes, I guess it's correct. So XG, how is it different from XG? Okay.
X I can give a counter example for XG. A path which doesn't satisfy that. Oh, no.
Yeah, go ahead.
No, I'm confused with the notations.
No. XG of AB is equal to 0. It is yeah. I think a more interesting question. Of course, you've already answered this. There is a path. So you know, this particular path starting from, like you said, 0, 1, 1. Okay, starting from 0, 1, 1, which only has a reset is equal to 1. If you consider that, then it's a path for which AB is equal to 0, 0 forever. Okay, what will be interesting is this obviously is not true for this particular model, correct? Because if you interpret this as an LTL formula, I think we are getting ahead. Okay, this is fairly good. First I wanted to introduce it informally, so you get the picture. I hope, okay, that you should understand this exercise was mainly to make you go through, start thinking about how you, to make sure that you understand how you interpret these the formal semantics of the CTL formulas. Okay. Then what I want to go through next is, let's see. So see, it's one. Yeah, I mean, you could. One way is given certain formulas, whether they are true for the thing or not. So let me now shift gear and so what is this? I want to go to this file and not start from I'll return to these negation normal forms, etc. So now I'll introduce you to some sublogics. Okay, so that. So computation tree logic is a sublogic of CTL star. So informal definition of this thing. See, all these sublogics are partly motivated. These sublogics are defined, and that is true for any, that's one of the motivations for considering any sublogics, because the model checking problem is complexity-wise simpler for these sublogics, and these sublogics have certain interesting properties by themselves. Okay, and those are the two reasons why we look at sublogics. Okay, so computation tree logic, CTL for short, is informally, it is a sublogic of CTL star where the path quantifiers and temporal operators, they always occur in pairs, okay, and adjoining, okay. So formally, it is defined as a logic which has the following subset of the formulas belonging to CTL star, okay. So if it's an atomic proposition, then it belongs to CTL. If F is a CTL formula, then negation is a CTL. It belongs to CTL, and all these these are called sometimes called CTL operators. Okay, the syntactic restriction is that every temporal operator in the formula has to be immediately and necessarily preceded by a path quantifier. So you can have AX, AF, AG, EX, EG, EF. Okay, applied to a sub CTL formula. Okay, so that is the restriction. Specifically, I mean, you can't use repeated temporal operators or other logical operators before you apply the quantifier, use the universal and existential quantifier. Okay, so that's what CTL is defined as. But of course, you could take conjunction and disjunctions of CTL formulas. Yeah, I think I should have included AU. I mean, these I've separated them because these are unary operators, and you can do you can take conjunctions of CTL and disjunctions of CTL, as well as use the until operator. But of course, an until operator has to be immediately preceded by A as well. Okay, A or U, similar. So basically, every temporal operator has to be immediately preceded, by an A, okay, or one of the quantifiers. Okay. Yeah. So another way to view is, if we want, by saying that it's a subset of CTL star formulas which are generated by the following CTL operators. Where CTL operator is something considered as a temporal operator immediately preceded by either the A universal path quantifier or the existential path quantifier. So an example. I mean, let's take a few examples to illustrate what are some legal CTL formulas and legal CTL formulas. Okay. So is this as per the rules that I've defined, is this a valid CTL formula? Ratnakar?
Yes, I think so.
Well, think again, okay?
No, right.
Because, yeah, it is not, because, see, as you say, we don't allow these, but disjunction and conjunction can only be used on CTL formulas, okay? So here, which are, so here you can't split like this, okay? So A, you cannot split over disjunctions of part formulas, okay? So you will have to see, look at this rule, the third bullet. So you are allowed to take conjunction and disjunctions only over CTL formulas which are recursively defined. So it does not allow you to take conjunction disjunctions over path formulas, okay, before you apply A. So this one is not a legal CTL formula. It forces you, the syntax, the constraint forces you to, it does not allow you to take disjunction and conjunctions over. That is one restriction. About this one, Paramalai? So here A is, assume A as an atomic formula.
So this is a proper formula in CTL.
Yeah, and why? Because A itself is a CTL formula. EX of A is a CTL formula. Because EX is certainly a CTL operator. And, because E and temporal operator appear juxtaposed. And so you can take conjunction over CTL formulas, after which you can apply a CTL operators. Yeah. So this is a well-formed CTL formula. About this one, Amin?
Yes.
Correct. And the reason is
So
that, yeah.
if like E of F until G is a CTL formula.
Yeah. So here I'm assuming F and G are CTL formulas. Okay.
Yeah,
So given F and G are CTL formulas, because you are, so you're applying a temporal operator, but then you are, I'm sorry, F and G are actually, no, I mean, F and G have to be part, obviously, yeah, because F and G are CTL formulas, because they are state, formulas, because they have to appear. Therefore, they automatically, state formula can be viewed as path formulas. Therefore, you can apply the until operator, and therefore, E is immediately preceding U and A. So this one is, okay, so you're correct. Okay, Ratnakar, about this one?
It's not, because you can't construct.
Yeah, because G, you're applying two temporal operators, without any intervening thing. Okay, so that is the restriction. Okay, so you will have pretty much two things. One is you have to precede every temporal operator immediately by a path quantifying operator, and you may not do logical connectives over temporal operators before you apply the path quantifying. Okay, so ACTL is a sublogic of CTL. I have not introduced a negation normal form. Yeah, informally, negation norm is restricted to using only universal CTL formulas. Okay, so it's a subset of CTL in which E is not permitted, and the negation operator has to appear only at the atomic, at the leaf level. Okay, that's how ACTL. And ACTL star is the sublogic of CTL star in negation normal form. I haven't formally introduced negation normal form, but informally a negation normal form. Actually, a negation normal form, that is, it is a general normal form which for proposition logic or any logic in which the negation operator appears only at the leaf, can only be applied to atomic propositions. Okay, so ATL star is something which in which you allow for CTL star, but only universal operators, universal quantifiers is allowed. Yeah. So these sublogics, as I mentioned before, are motivated by the fact that they have interesting properties that permit efficiently tailoring model checking to the sublogic. Okay, so I'm introducing these things even before we study the model checking problem, so that you get acquainted with these logics, both in terms of in understanding what those formulas belong to this logic are, and then given a certain property whether you could express how to describe them, how to formulate them in that particular logic. And those are the two things that I expect you to somewhat get acquainted and master over during the course of this course. Okay. So linear temporal logic, informally, it is the sublogic of CTL star by restricting CTL star only to only a subset of its path formulas, in which the path quantifiers, no path quantifiers are not permitted. Okay, which means the P belongs to, if it's an atomic proposition, then it belongs to an LTL. Then it is an LTL formula, because although this is a state predicate, as you know, a state formula can always be, we have a way, a convention to interpret them as a path formula. And if F is an LTL formula, then you're allowed to take negation of it and then apply any of the unary temporal operators to that LTL formula. In FNG or LTL, then you can do all these binary operations. You can take the logical conjunction and disjunction over two path formulas, two LTL formulas, and you can take use the temporal operators until and the until and the release operator. So now for CTL, okay, I did not define the model checking problem for CTL, but since CTL is obviously every formula belong to CTL is a state formula. Therefore, the model checking problem for CTL is just defined just as you would define for CTL star. Okay, since every formula CTL that belongs to CTL is a state formula, whereas here, we need to define. We need to define the what it means for the model checking, because the model checking problem is defined as a satisfaction problem of a formula by a model with a Kripke model with an initial condition. So if I belongs to an LTL formula, and then we say that a Kripke model satisfies an LTL formula, yeah, technically, informally, every path starting from any of the initial states must satisfy, every path satisfying from any of the initial states must satisfy that the formula, the path formula phi. Okay. So which is, in other words, if you put the a universal path quantifier at the topmost level only for the formula phi, this should be phi. Okay. F, there's a mistake here. Read F as phi, then M should satisfy that as a CTL star form. Okay. So in other words, so yeah, so that's what it is. So an LTL formula implicitly, when viewed as for the purpose of model checking satisfaction, is assumed to be universally quantified at the top level, okay, and then viewed as a CTL star model checking problem. That is, informally, as I just now described, phi holds in M if it holds for every path pi from every initial state of M. So that's how it is defined. Okay. So do you understand this? Any questions here about the satisfaction problem, the LTL satisfaction? I mean, satisfaction as well as the model checking problem. Okay. Yeah, this is an aside. Okay. So having, yes.
I have a question. I couldn't find the difference between CTL and CTL star because both of these restrict that the formulas should be state formulas. All the formulas contained in them should
no, I just gave an example. For example, okay. So this one is a CTL star formula, but not a CTL formula.
Okay. So
I mean, it's true that both CTL and CTL star, at least for convention, we have defined that as a state formula. Eventually, it must be a state formula. But that aside, so it is the way CTL restricts the way that you construct your state formulas. That's all.
Okay.
So you can have in CTL star, you can have any path formula as a sub-formula of that state formula, okay? Whereas CTL does not allow it. So specifically here, one of the things that it doesn't allow is you can't use logical connectives over path formulas before you apply a path quantifier, or you can't use repeated temporal operators before you apply a path quantifier, like in this case. So for example, f of g of a. I mean, if I put an a around this, that's a CTL star formula, but not a CTL formula. Okay. Those are the two important distinctions. Yeah. And apply logical connectives to path formulas before you apply the quantifier, CTL, nor can you do these kinds of things before you apply.
So our model checking system, like new SME, does it restrict us to use any one of these? Like we have to use only CTL.
Yeah, I think so. I think the new assembly supports, it certainly support. Yeah, it is. I think here I may be correct. You can check it. I don't think it works for CTL star. Okay, it only works for LTL and CTL. Okay, you can check that yourself. Here I'm claiming that. Why don't you go type up a CTL star formula to new SMV and then see if it accepts it or not. My hunch is that it does not. Okay. So, but it does support both CTL model checking and LTL model checking, yeah, separately.
Okay, sir.
Okay, so what is the time now? So am I 1 o'clock when I have like 5 more minutes, I guess. No? Okay, which one should I do? So, yeah. Yeah, this aside is what I'm saying, okay? So obviously, so LTL model checking, for the purpose of LTL model checking, it is as though there is a implicit, universally quantified path quantifier at the top level. And then you can interpret that as the traditional model checking in CTL star. The question is, I mean, does that mean that you cannot do E of some phi, where phi is an LTL formula? You can do that, because as long as you only have existential quantifier at the top level, that is the same thing as checking if that the model does not satisfy A of not of phi. Okay, think about this. Okay, I will let you think about this. Okay, so you can have limited E of phi model checking capability. Okay, so I mean, this is something that that you need to understand a little bit more, LTL and model checking. Okay, so you can do one level of existential quantification at the top level by actually checking that A of not of phi, because E of phi is satisfied this is what is called as the existential LTL model checking problem. Okay, of checking if there exists, if you want to check if there exists a path that satisfies a particular LTL formula starting from an initial state, you can do the same thing by actually showing that A of not of phi, the negation of the LTL formula, that does not exist for every path originating from every initial state, violates in the model, violates not of phi. Okay, that is one way of checking E of phi. Okay, so at least you can do do that. Yeah. So what I want to do here is, since you have already done, I will let you go through this. Okay, these are toy examples which are actually taken from Beethoven. So maybe I will. Let's go through this so the end of the class. Since you've already seen what CTL star formulas are, this should be pretty easy for you. But since we are at the end of the class, and since our brains are a little bit overloaded, let me go through this thing anyway. Okay, so here is a toy Kripke structure. I've deliberately left consider that every state in the Kripke structure can be an initial state. Okay, so but I'm asking this question. So these are some LTL formulas. Okay, so you notice that I've only used LTL operators or and no quantified formulas. Okay, for each of them, I want you to answer whether there exists a state in this Kripke structure from which, okay, I'm asking you, give me all the states in the Kripke structure such that every path from that state satisfies the LTL formula, or there exists a path starting from that state that satisfies this formula. Okay, So that is what I want you. So let's go through that exercise because this is good. Good kind of mental exercise for you to make sure that you understand. Okay. So you understand my question, right? So I will start with Ratnakar. XXY.
I think for all should be empty, and their exist should be 2, because you can get from 2 to 1 to 3. 2, 1, 3, 2.
It's been, yeah, okay. XXY. So from 1, let's look at each state. So from 1, I mean, how did you answer that so quickly? So next to next is what it's saying. So from 1, next to next, Y is true. Yeah, those are the only paths. No, that's actually not true. So next to next is true.
Actually,
Yeah.
I was wrong. I think 1 satisfies for all and 1 satisfies their exist, and I don't think 2 satisfies their exist.
So I have CTL thing. So let's see what the. Oh, I don't have answers for this. Maybe I will. Okay, so let's just do CTL. So let's do sum. Okay, for each. So what is the answer? So let's look at what are the paths starting from 1. Okay, so every path starting from 1 has to go. Okay, there's 1. I mean, here of course we are infinite. What are the paths? There's 1, 3, 2, 1. Okay, that is one looping path. Correct. 1, 3, 2, 1 repeating itself, or 1, 3, 2. Every infinite path starting from 1 has to go through 3 and 2. After that, you have to cycle, forever into 4, or you can do some finite number of times. You can loop in 1, 3, 2, and after that you can loop here. Okay, or you can repeat it. Yeah, you can have finitely many times. You can do this and some finitely many times, and then eventually you have to repeat that. Correct. So I think your original thing was correct. Okay, why did you take that? Because every path that originates from.
I have some confusion on how you interpret Y. Do you interpret, if Y is true, do you interpret it to be, does that mean that it's true for every single state or suffix on that path as an atomic proposition?
No, why should the label Y should belong to that state, or which is the same thing as saying Y should be true in that state. Now, for example, if I say R is labeled with R, what it means this: R is true, Y is not true, and G is not true. Okay. I mean, yeah, that's how I interpret. Okay. So here, when I say R is a label of 1, which means that R is true, Y is not true, G is not true. And in state 2, Y is true, G and R are not true. That's how I interpret. So viewed as labels, it belongs to that label means, okay, yeah, that's how it's interpreted. Now here, yes, does that answer? So if I had labeled 1, I mean, as R and G, that means R and G would be true and not. Okay.
Okay.
That's how it should be interpreted. Because XXY, because every path originating from 1 has to have a prefix, okay, in which the prefix 1, 3, 2, correct? So, and XXY is true, since it has every path XXY is true. Yeah. So both are true. Okay. So let's do XXR.
2 also satisfies their exist, right? Because 2
Yeah.
can go to 4 and back to 2.
Correct. So the paths going from 2, they're of 2 kinds. One is you go to 1. No, that's actually not true, because see, there is a path from 2. Okay. So 1 certainly satisfies this for all, and therefore by extension exists. So what did you say? 2
I
also
asked if 2
satisfies.
their exist.
2 satisfies their exist, yes, but not for all. Correct? Because, see, for example, the path starting from 2 goes 2 to 1 to 3 does not satisfy XXY. Because 2, 1, 3, because state 3 does not satisfy Y. And that's why not every path originating from 2 satisfies that. But of course, there exists a path starting from 2 that satisfies this LTL formula, and that path is this one, 2, 4, 2, where you loop. It's 2, 4, 2. Or for that matter, any path that starts from 2, goes to 4, goes back to 2, then you can loop. Okay? It's only this path, 2, 1, 3, that does not satisfy. Yeah? Okay, that is the answer for that. There's an LTL thing. So XXR, anyone want to? Well, let's do GFF of Y. Amin? Let's do this. Does every path originating from state 1 satisfies this? First of all, what is G of F of Y? Let's
G of f of y means like every state in the path like should eventually reach to a state y, like eventually meet a label y, right?
on every path. Okay, so let's first do F of Y. Amen. So let's start with F of Y. Okay. So Y is an atomic proposition. F of Y is true of any path in which Y there is a
y. Like
yeah, there is a
eventually we
future
reach a
point at which Y is true. Correct.
Yes.
So what is G of F of Y?
G of f of y, like in every state it should be true. In
Yeah, at every
state that
every
f
suffix
of y should be true.
yeah, F of Y should be true. Okay, which means it is something like this. Okay, so here I have illustrating it for it really is infinitely often. Okay, so it is saying that F of Y should be true at every suffix of that path. Okay, so what that means is that is for every point on a path there must be a later point at which Y should be true. So what that means is, you know, that for every point on the path, F of Y should be true. which means that, you see, I mean, if y is true at some particular point, then it is true for all these suffixes starting from this, that gets taken care of by that. But g of f of y insists that it has to be true even for this one. So there must be a future point. So effectively, what this means is this is what is called an infinitely often. Okay, what I informally, when you say some event should be true infinitely often, this is what it means. So y should be true infinitely often. So g of f of something, some condition, means that that condition must be true infinitely often. Okay, so having said that, okay, let me now go back to this example. So we are looking at this. So does y occur infinitely often on every path starting from state one? Amin? Yeah, complete. Yeah.
Yeah, it does, right?
Why? Because
Like every path from one will like meet to infinitely often. Right. Actually, any path starting from any state will meet to, right? Always,
no, let's
because
do
it's
for
in a
one.
cycle.
Let's, yeah. Yes. Okay.
Like,
You're right. Okay, that's a very good point. Yes. Yeah, because every cycle in this passes through the state 2, correct? So, and in which 2 is true. Therefore, you're right. Okay. So that's why g of f of y is true for starting from any state. Okay. So that is true. The point, because that is because every cycle in this must contain the state 2, okay, in which y is happens to be true. Okay. Okay, so let's now, as a, we're running out of time, so I just want to not let Paramalai get away. Therefore, let's look at this one, until operator, be until not be.
So the state 4 satisfies this property for every operator. Every path starting from the state 4 will satisfy this property.
Why?
Because the state has a B to be true, and the next state it goes, no matter any state.
Yeah. So what are they? I mean, just to be clear, what does until require? Until has 2 requirements. Okay, if you remember correctly. Okay, that eventually, I mean, this is true of any path in which eventually, that is, eventually f of not of b should be true. Okay, but eventually b should become false, not b. You should get to a state in which b is false. Up until that point, b has to be true. Okay, so b until not b is really like not b, f not b. Okay, yeah, and that's why what it is it requires, it imposes that not b should be true. Yeah. So why is it true for yeah, so yeah, complete your argument.
So yeah, my argument is this: every path starting from the state 4
4.
will eventually get not B.
Correct. Yes, because it
And
has to go through 2. Okay.
yeah,
So every infinite path starting from 4 will have to go through 2, in which not B is true. So this is a bit superfluous. Okay. So B until not B is actually equivalent to F of not B. Do you agree?
I have a
Sir,
question here.
Yeah.
yeah, that is not true, right? Yeah, so
It is not true for one.
continue.
One at a time.
I
Yeah.
was saying that f of node B, it is not equivalent to f of node B, right? Because one more constraint is there that such that like till node B is reached, like B should be satisfied in the path. There are 2 constraints, right?
Yeah, but
Eventually node B should be true. Also, till node B is reached, B should also be satisfied.
But why
in all the
will
states.
if not B is true at some point, and the earliest point in which it is true for all the states before that B is necessarily not. Wait a minute. Okay, I'm getting confused. Yeah. So if not B becomes false at some point. Okay. Look at the earliest point at which not B is true. Okay. So what does B until not B means? So B.
Yeah. Now I
Yeah.
get it.
So no.
yeah,
So
you're
B
right.
has to
Sorry.
be necessarily true. So that's why it is equivalent.
Yeah.
Look at
Yes.
that.
Yes.
Yeah. So this is a bit of
This
a
is mainly because it is B until not B, right?
Yeah.
Like, yes.
Okay, so we'll stop here. Okay, so what I will do is I'll upload this without. I want you to go through some of the things. Okay, 2 things that I want you to do. So maybe if I think I don't know if I have answers to this. Oh, I don't. Okay, yeah, good. So try this. I mean, it's actually in the Katovan book, so you might as well, without actually looking at it, maybe you want to try this. Okay, and I also want you to go through this. So remember that I had. Oh, I'm way out of time. Sorry. Where was that I had? So remember that. I will upload this also. So I want you to look at these things and express each of them. Here, what I have is some properties which are actually described kind of in first order predicate calculus, okay, to make it precise. But I want you to convert them into an LTL or a CTL formula, okay? So these 2 exercises informally I want you to do before next class. And we will, yeah? Okay. So any questions you have? I mean, I know it's very late, so maybe you can take the questions later on. I'm sorry that I went way beyond my